Hello students, welcome back to Rasayan. Under application of resonance or mesomeric effect, in my previous videos I have explained about stability of carbocation, stability of carbon ion, stability of free radical. Now I am explaining about how to compare the acid strengths using resonance or mesomeric effect. First I will explain why phenol is acidic. For that, you draw resonating structures of phenol. There are 5 resonating structures. Now see, in the resonating structures of phenol, there is positive charge on electronegative oxygen and negative charge on electropositive carbon. And also there is charge separation. Now see, these are resonating structures of phenoxide ion. Here there is only negative charge on electropositive carbon, and also here there is no charge separation. So phenoxide ion is more stable than phenol. Phenol, by removal of H plus, will generate phenoxide ion. This is conjugate base of phenol, and we have seen phenoxide ion is resonance stabilized. It is more resonance stabilized than phenol. So if conjugate base is more stable, then parent acid is acidic. That's why phenol is acidic, because conjugate base is more stable. Next is, between carboxylic acid and phenol, which one is more acidic? So first what you have to do, take the acid, remove H plus, you will get the conjugate base, the carboxylate ion of carboxylic acid. And here it is having equivalent resonating structures. Due to that, the species is stabilized. Now what is about phenol? Take phenol, remove H plus, you will get corresponding conjugate base, phenoxide ion. And we have seen there are 5 unequal resonating structures. 5 unequal resonating structures. So between carboxylate ion and phenoxide ion, which one is more resonance stabilized? It is having, since it is having equivalent resonating structures, that's why it is more stable. This conjugate base is more stable. Therefore, corresponding acid is more acidic. Therefore, carboxylic acid is more acidic than phenol. Next question is, between phenol and alcohol, which one is more acidic? Take phenol, remove H plus to get the conjugate base. Take alcohol, remove H plus to get this conjugate base. It is called alkoxide ion. Now see, this phenoxide ion or phenolate ion, it is resonance stabilized. Resonance stabilized. But in alkoxide there is no resonance. Take methoxide for example. Here due to plus I effect, magnitude of negative charge on oxygen is increasing. So it is not stable species. This conjugate base is more stable than this one. Therefore, corresponding acid will be more acidic. Therefore, phenol is more acidic than alcohol. Now compare the acid strength between acetic acid, benzoic acid and formic acid. For that, you have to write the structure of the conjugate base of the corresponding acids. This is acetate ion, this is benzoate ion, this is formate ion. You know formate ion, it is having equivalent resonating structures. So next resonating structure, this one. So here there is equivalent resonating structures. That's why formate ion is stable and formic acid is strong acid. Now if you compare the acidic strength between this and this, now you draw the structure of benzoate ion. Here also this negative charge will be stabilized by resonance like this way. At the same time, this pi bond of the benzene ring is in conjugation with carbonyl. All pi bonds are in conjugation with the carbonyl group. So here resonance is possible, and due to this resonance between CO and benzene ring, O minus is less involved in resonance with carbonyl group compared with this. Therefore here negative charge density on oxygen or magnitude of negative charge on oxygen is increased than this one. So this is less stable conjugate base than format. Therefore between these two, which one is more acidic? Formic acid is more acidic. We know the more stable the conjugate base, the more acidic is the corresponding acid. Now how to compare between acidic nature of acetic acid and benzoic acid. Acetate ion structure is this one. CH3 is having plus I effect. Due to this plus I effect, it will increase the electron density on O minus. So it will destabilize this conjugate base. But here see, this carbon is sp2 hybridized. This double bonded carbon is sp2 hybridized. So it is having minus I effect. So it will pull electron density in this direction. So negative charge density of oxygen is decreased. Means this conjugate base is more stable than this conjugate base because it is destabilized by plus I effect of CH3, and here it is comparatively more stabilized due to minus I effect of this double bond. So if it is more stabilized, then conjugate base is more stable than this conjugate base and corresponding acid is more acidic than this acid. So we have seen when we are comparing the acid strength between benzoic acid and formic acid, we have to consider resonance effect. This resonance effect between CO and benzene ring. And when we are considering the acid strength between acetic acid and benzoic acid, we have to consider the plus I effect of methyl and minus I effect of this double bonded carbon. Now see, this is substituted benzoate ion. If you want to compare the acid strength of substituted benzoic acid, you have to remember electron withdrawing group, means which will abstract electron density, it increases stability of this benzoate ion, and if G is electron donating group, it will give electron density. So what will happen? It decreases stability of benzoate ion. And always remember, ortho substituted benzoic acid is most acidic than metapara isomer. This is due to ortho effect. But there is some exception. For example, when NH2 group is present, amino group is present, there is no ortho effect. No ortho effect. So what is ortho effect? Suppose you are having substituted benzoic acid, where here ortho substituent is there, maybe G is equal to alkyl group, or maybe G is equal to nitro group, all those. So here steric crowding will takes place if here ortho substituents are there. Due to this steric crowding, COOH group and benzene ring are not in the same plane. So resonance is not possible here between this carboxylate ion and benzene ring. If resonance is not possible, as we have seen earlier, if with this carbonyl and benzene ring resonance is not possible because they are not in the same plane, then what will happen? This O minus will be stabilized by resonance with carbonyl group. So it is stable and corresponding acid will be most acidic. With one example I am explaining. This is called ortho effect. Now compare the acid strength of ortho, meta, para, nitrobenzoic acid and benzoic acid. Now see, nitro group at para position, it is having minus I effect and minus M effect. Nitro group at meta position, no mesomeric effect, so only minus I effect. And here you know ortho effect is there. So what we have to do to compare the acid strength, first we have to draw the structure of conjugate base of the corresponding acid. So this is carboxylate of paranitro. This is metanitro. This is orthonitro. And this is for unsubstituted benzoic acid, benzoate ion. Now due to minus I and minus M effect, both are electron withdrawing. So para carboxylate ion is more stable than meta because here only minus I effect is there. So first, due to ortho effect, this ortho carboxylate ion is most stable, so corresponding acid is most stable. Next, between this and this, which one is most stable? Here, due to these two effects, this ion is more stabilized. Therefore, next is coming para. After that meta, then unsubstituted benzoic acid. This is the strength, acid strength order, decreasing order. Now see, next application of resonance is to decide basic strength order. Basic strength of amine depends on the availability of lone pair on nitrogen. If availability of lone pair on nitrogen is more, it is more basic. If availability of lone pair is less, compound is less basic. Now see, between ethylamine and aniline, which one is more basic? Now see, for aniline, lone pair on nitrogen is in conjugation with pi system of benzene ring, because you see lone pair, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond, like that way conjugation is there. So this lone pair is involved in resonance. You can break this bond and you can get next resonating structure. So due to this resonance, lone pair of electron, it is less available for donation. And here C2H5 group is having plus I effect. Due to this plus I effect, electron density on nitrogen atom will increase and it will donate more easily than aniline. So which one is more basic? Ethylamine is more basic than aniline. Find out the basic strength order of these three compounds. This is first one is benzylamine, next is aniline, last one is diphenylamine. So in benzylamine, nitrogen lone pair is not involved in resonance with benzene ring because it is not in conjugation. Lone pair, single bond, then double bond. So there is no resonance. Here resonance is involved between lone pair and pi system of benzene ring. So resonance is there. And here with nitrogen, two benzene rings are attached. So more resonance. Therefore here it is most available, then this one, then this one. Obviously basic strength will decrease in this order. This is least basic because nitrogen lone pair is less available here. Now find out between pyridine and aniline which is more basic. You can see in pyridine it is having 1, 2, 3, 4, 5, 6, 7, 8 electrons. But out of these 8 electrons, these lone pair of electrons on nitrogen are not involving in resonance. Why it is not involving in resonance? Because this nitrogen is sp2 hybridized. Nitrogen is having valence shell electronic configuration 2s2 2p3. Here in sp2 hybridization, these are sp2 hybridized orbital, this is unhybridized p orbital. So here electrons are like this, means lone pair of electrons are in sp2 hybridized orbital. Here for pyridine, lone pair of electrons are in sp2 hybridized orbital. Therefore, lone pair on nitrogen and unhybridized pz orbital of carbons, unhybridized pz orbitals of carbon, they are perpendicular to each other. Therefore, resonance is not possible. So, it is having, pyridine is having 6 delocalized pi electrons. This is 4n plus 2 pi, where n is equal to 1 pi electrons. So this is cyclic, planar and having 6 delocalized pi electrons. According to Haeckel's rule, this is aromatic. So to maintain aromaticity, it doesn't need this lone pair of electrons. These lone pair of electrons, since it is not involving in resonance, are fully available for donation. But what is about aniline? Aniline, you see this part, benzene ring. It is cyclic, planar, having 6 delocalized pi electrons. It is aromatic. Due to this part only it is aromatic. And nitrogen lone pairs are involving in resonance. Why nitrogen lone pairs are involving in resonance? Because lone pair of electrons on nitrogen, they are at 2p atomic orbital. So these lone pair of electrons are partially involving in resonance and partially available for donation. You know how it is involving in resonance. Like this way you will get resonating structures. So since this lone pair of electrons are in 2p atomic orbitals which are parallel to the unhybridized p orbital of benzene ring, therefore resonance is possible. Therefore these lone pair of electrons are partially involving in resonance and partially available for donation. And here it is fully available for donation. So between these two, pyridine is more basic than aniline. Basic strength. This is basic strength. Order. Now see, between aniline and pyrrole, which one is more basic? Here nitrogen is sp2 hybridized. Unhybridized p orbital is having lone pair of electrons. Okay. So lone pair on nitrogen and unhybridized p orbitals are nearly parallel to each other. Lone pair on nitrogen and unhybridized p orbitals on carbons are nearly parallel to each other. So here resonance is possible. If here resonance is possible, then see how many pi electrons are there then? 1, 2, 3, 4, 5, 6. 6 delocalized pi electrons are there. It is cyclic, it is planar and having Huckel's number 4n2 plus 2 delocalized pi electrons are there. Therefore, it is aromatic. So, lone pair of electrons are involved to maintain aromaticity. These are less free for donation, but here for aniline, lone pair of electrons are involved in resonance, but they are not involved to maintain the aromaticity. Therefore, these are more free for donation. So, between aniline and pyrrole, obviously aniline is more basic.